mean, first of all, welcome. Thanks for participating. That's always what I start with. This is an hour long, right? In a real interview, it'll be an hour as well. But in the hour, you'll usually have about 45 minutes to maybe 50 minutes for the actual problem solving. We'll just dive right into that, right? So we'll just get right into that today. We've got one problem. If we were fast, maybe we'll do two.
Okay,
And then afterwards, we'll do questions, feedback, etc. How's that sound?
sounds perfect. Thank you.
Okay, great. So let's just start with a problem here. This problem is gonna be called group anagrams. Have you heard of it?
Um, I've heard of anagrams before.
Okay, so let's do this problem. So it's called group anagrams. All right. So
Okay,
I'll dictate the problem, and you can go ahead and write down the notes. You can ask me any questions you need. So
okay,
this problem called group anagrams. The input to this function. So I want to write me a function called group anagrams. The input
okay,
is going to be a list of strings,
okay,
and the output is going to be a list of strings. Okay. And the goal of this function is very simple. It is to group all the words together into one list, such
okay,
that all the words in the list are anagrams of each other.
okay.
Do you know what an anagram is?
Yeah, it's just that you could order the letters in any way, right? And then I guess that would be like the same word, I believe.
Yeah.
Okay, okay, okay. Um, so I guess I have heard of this umpire framework, so maybe I'll try that, and then we can maybe get some feedback on how that works for technical interviews.
Okay.
So just to make sure I understand the input is, I guess, a list of strings, and then the output is a list of the strings. Um, and then, yeah, I guess these are just different words, and then we have to order them into a list of strings. Right, okay, that makes sense. By their anagrams, so common anagrams. So I guess maybe I could start with some assumption slash clarifying questions. So first off, I guess, can I assume that the input list is always existent, like it's not empty?
It can be empty.
Okay, um, input list empty. And then can I assume that the strings only have characters, like they don't have numbers or spaces, like it's just single words?
Yeah, you can assume that.
Okay, single words, only characters. Can I assume that it's only lowercase characters, or could it be lowercase and uppercase?
They can be any ASCII, alphanumeric characters, or not numeric, just alpha characters. So okay, upper and lowercase. Yeah.
Okay. So if I have, like, for example, the word hello and like, for example, would this be considered, or sorry, let me just make that lowercase. Would this be considered an anagram? Like, should we do case matching or not?
So that case should not be considered an anagram.
Okay, so I'll say case sensitive. Okay. Um, okay, so I think that's maybe all my clarifying questions for now. I could maybe clarify later. And then I guess example, maybe test cases just to confirm I understand. So if we have, like, for example, hello, um, Ali, Ali, and maybe like that, for example. So I guess the output for this one should just be a list of hello. So just to confirm, would this be the output to that input?
Yep, that would be invalid output. Yep.
Okay. So I guess I could maybe move on to the next step, which is where I think of some approaches. Um, so I guess maybe my initial approach would be to maybe sort each word. Um, yeah, I think I would sort each word and maybe use a hash map to check for existence. I would sort each word, have that be the key, and then have the values be, if when sorted it matches that key. So I guess if I were to write that down, I would just say sort each word, use hash map to check for existence, um, and values is list of the words. Though I'm assuming that's the intuitive solution or the naive solution, because I guess for each word we would have to go through them. And if we say each word is of length n, then that means we would have to sort each word, and then let's say each word is of length k. We would have to sort each word and do that n times. So I don't think that would be too efficient. And then I guess the space complexity, I guess would be the entire list as well. So there's probably a better way.
Mm-hmm.
Okay, so I guess maybe alternatively what we can do is, you said it would only be ASCII characters, right?
Yeah,
Like uppercase and lowercase. So
that's
maybe
right.
what we can do is we can still use a hash map, but instead of sorting it, and since there's no spaces, so since it's individual words, we could just maybe get the frequency of each letter. And then, yeah, I guess we can just check the frequency of each letter, and then if there's a key that exists with that frequency. So I guess the frequency could maybe be a frequency of, I guess, 26 times 2, just because there's lowercase and uppercase characters. So we could just have the frequency, and then that's the key. And then the value is going to be the words themselves from the list, right? So I guess if we were to think of the time and space complexity of this one, we're iterating through each word. And then when we're iterating through each word, we only have to do a single pass to find the frequency, check if that frequency array exists. If so, then append to that list. Otherwise, create a new list and append to that list. And I guess the key itself would be of static size because the number of, I guess, letters in the alphabet doesn't grow with the input. And then I guess the space complexity would also just be O, and I believe just because of the hash map. So do you think maybe approach 2 is a good solution to proceed with?
Yep, I like approach 2.
Okay. So I guess I'll say just for plan, implement approach to the hash map, and then to implement. So I guess what we can do here is you can have a default dict first. So I'll just say, or I guess I'll create the function first. So I'll say def group anagrams, which takes as an input a list of strings, which you can just call words. And then I can create the dictionary. So for the dictionary, I'll just call it frequency for now, and I'll make it a default dict of type list. So we don't have to create that list. And then I guess I have to import it. So I think it's import, or I think it's, sorry, do you know what the API or the collection library is for default dict? Is it just collections?
Yep, it is.
Okay, so from collections, import default dict. Okay, thank you. And then once I do that, I guess I could have I could just iterate through each word. So I'll just say for word in words. Then I have to iterate for each character in word to first create that key or find a key. So for character in word, and then for each character, I would like to find or determine that key. So I guess before I do that, I'll create a list. So I'll just say here char frequency, which equals, let's just say initially they're all equal to 0 times 26 times 2, which is 52. And then I guess I could just map the ASCII values. So I believe what I can do is for each character, I can get the ASCII value like this. I'll say order C minus order A, and then just say that's I guess like the word belongs in the char frequency array if it's lowercase.
Okay.
And then I guess if it's uppercase, I would have to handle that separately. So maybe what I can do is I can check if it's lowercase or uppercase. So maybe I can say if C equals C dot. Is there a way to check, like, is there a lower function on a character? Like, can I do C dot lower? Does that exist?
You can assume it does.
Okay. So if it's lowercase, then index equals this. Else, we can say index equals the order of the character minus the order of a capital A, and then we'd have to multiply it or add some scaling factor. So I'll say index equals 0. And then if we do this, I think we can just say 26 plus this should work, right? Because this would map to indexes 0 to 25, and this would map from indexes 25 to 51, I believe, and both are of size 26. So once I do that, then I'll just say here frequency of char frequency dot append the given word. Though I guess sorry, I might not be too clear on this, but can we have a hash map with a key of a list, or would that not be possible since it's mutable?
That would not be possible.
Okay, so this approach is an issue. I guess maybe one thing I can do is once I generate all of this, I could convert char frequency to a tuple because that is immutable. So I think I can just say tuple and pass in a list. Would this be possible, converting it to a tuple and using that as a key?
You can assume that works.
Okay. And then once I do that, I believe I populated my hash map. And then I just have to return the output. So I can just say here, I guess I can just convert it to a list of lists. I'll just say here output equals a list. And then I'll just say for key val in freak.items. I'll just say here output append val, which is a list itself, and then return output. So I guess once I do that, maybe the next step would be to go through the tests just to make sure it works. So let's see here. I guess maybe we can just pass this and walk through the test. Any concerns or comments as of now, or is it good so far?
You're not using the index variable.
Yeah, I just realized. Okay, yeah, that's an issue. I have to update char frequency, of course. So I guess once I do that, I'll say char frequency at index plus equals 1. So I guess, yeah, that's actually me using the index. So it'll discount the frequency and increment it by 1. It's initially set to 0, so if there's more than 1, it'll just add 1. And then it'll find this for each one and append that word. Okay. So should I walk through an example test case now?
Yeah, you can pick one to go through. Yeah.
Okay. So first we'll take the word hello. We'll iterate through each character and then it'll create that char frequency. So I guess maybe you can focus on this bit here. So it'll be a bunch of zeros, and then once it finds h's this, so we can just say 0 dot dot dot, and then once it finds h, it'll have a 1. It'll have, I guess, like a 1 for an e, for example, and then dot dot dot, and then it'll maybe have 2 for the l, and then I guess dot dot dot. So where the dots just represent the zeros, then it would have 1 for that, and then it would just have dot 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 for all the uppercases and remaining letters. Then we move to LE. It should have its own frequency map. So if we can abstract and trust that this works, it would have its own frequency map. And then for lowercase LE, this would have a 1 at index 0, while this would have a 1 ideally at index 0 plus 26, which is index 26. So these don't match, so they'll be in separate parts of the frequency dictionary. And then for this one, hopefully this should have the same frequency as the first hello. So it should have this, since it has the same frequency or the same key, it would just be appended to the same value array. And then I guess after that, we can just iterate through the dictionary or the hash map, and we can check for all the keys that are the same, just append the value, which should be hello and hello backwards, and then Ali in the second list, and then Ali with the lowercase in the third list. So I think that would work with this test case. Is this good for the initial walkthrough, or should I go into more detail?
No, I think I'm okay with that. Yeah.
Okay, and then I guess just as a final step, we can just evaluate the implementation. So I think just to confirm, the time complexity was as we suggested, which was iterating through all the words. And then I guess we have to iterate through each character, so we can assume that the longest word is of k characters. And then the space complexity is also, I guess, just O of n, where n is the number of words. And
Okay.
yeah, I think that might be as efficient as it gets.
Okay. I'm happy with that. We can move on for now.
Okay.
Okay, great. So let's move to the second question. The second question is not related to the first.
Okay.
So this question is called find delay, find maximum delay. In this question, I would like you to write me a function called find delay, which returns the longest possible delay to travel between a given source node and the given target node. Okay? And so the input to this function will be a source node, a target node, as well as a representation of a graph which you can choose. So you can be, for example, an adjacency list, or a pair or list of edges, for example. So you can choose the type of graph representation, but you'll also be given an input node and a end node.
Okay. So I guess we could just clarify the problem first before starting. So just to make sure I understand the problem, the input could be graph representation of any type. So let's maybe say for now it's an adjacency list, which would I guess be like a hash map where the key is the source node and the destination nodes are in a list. And then the output would just have to be of type int, and that would just be the longest delay between source and destination node. Okay, is that correct?
Yep.
Okay, and then let's maybe just for the assumptions or clarifying questions. So I guess my first question, as usual, would be, can we assume that first off, the graph does exist, like it has the source and destination node, or could it potentially be empty or only have a source node or only have the destination node?
It must have at least both nodes.
Okay, so graph empty has both source and destination node. And then I guess so we have to find the longest delay, not the shortest delay or shortest path. So would the longest delay just be defined as the shortest path between source and destination node?
The longest delay is the longest path.
Okay, so longest delay is longest path. Okay. Let's see. And then can we assume that the source and destination nodes are just they're just numbers?
What do you mean by the number?
Sorry, so like would the graph just be a bunch of nodes where each of the nodes are just a simple integer number, or would it be like, for example, strings or anything else? What's the data type of each of the nodes?
You can pick.
Okay, maybe we can just assume ints for now, for easy comparison. Okay, and I guess so for an example input, let's say we have a hash map where we have a key of, I guess, 0, which maps to 1, 2, 3. Then we can maybe have 1, for example, which goes to 2 and 3. And then we can maybe just say 2, which goes to 3. And we can say the source node is of type int, which is 0. The destination node is of type int as well, which we could say is maybe 3. So I guess in this case, maybe the output would just be from 0 to 1 to 2. I'm sorry. So 0 to 1 to 2 to 3. So the output would be, I guess, the longest delay. So when you say delay, would it include the arrows, right? Not necessarily the nodes. So in this case, the output would be 3, not 4.
Yeah, it would be 3. Yeah.
Okay, okay. So I guess even though they could have gone from 0 straight to 3, we want to find the longest path. Okay. I guess maybe we can try to match this to an approach or a data structure. So obviously we have a graph, so we would use DFS or BFS. So I guess since we have the flexibility to choose either or, maybe what we can do is we can do an iterative BFS where we start at the source node and try to, I guess, yeah, just go to every node from there and every node from each of those nodes or from each of the neighbors. And the iterative BFS would have a queue or a data structure, which would keep track of the, I guess, like the current node and the number of delays thus far. And then I guess we would check if we found the destination node while popping from the queue. We can just update the max delay if it's greater than the existing delay, and return the max delay. So I guess with this solution, the idea is that the time complexity would be to iterate through all the vertices and edges, and the space complexity would be to the queue would store all the vertices, I believe, in this adjacency list. So I would only store these numbers in both queue and, of course, the scene hash set. So we'd, I guess, also have like a scene set to make sure that we don't go to the same node twice.
Okay.
Do you think this solution is viable or should be implemented?
We can go with this. Yeah.
Okay. So I'll just go ahead and implement this. So I guess we can just implement maybe a traditional BFS and then go from there and customize as necessary. So we'll have a queue which equals a deck, and I guess I'll have to import it. So from collections, import ID deck. So from deck we'll start with an iterable, and the iterable would be the source node. And then I guess it would also store the number of delays thus far. So I'll just say source node and 0. And I guess, sorry, this should all be a function. So I'll just say def find delay. So it takes a source, a destination, a graph. Okay, so we have that initial queue. which starts with the source node, and then we'll add that to the scene hash set as well, so we don't revisit that node later. So again, that would, I guess, I think in scene we would just track the node, so we can just have that initial source node. And then I'll say here while queue, so while there exist nodes in the queue, we can pop the current node and the number of delays from the queue, so dot pop left, which would pop from which would pop in a FIFO fashion, I believe. And then we would just say if node equals a destination, because it's just integers. If so, then we would update the max delay. So I'll say max delay equals float. So since the max delay, I could maybe start with a negative infinity. And then since I start with negative infinity, I can just say here max delay equals the max between max delay and I guess the delays. And then I guess we would just return max delay at the end of it all. So the next step would just be to iterate through all the neighbors of the current node. So I'll just say for neighbor in graph node. So once we iterate through every neighbor, we want to check if it's in scene. So I'll say if okay, I guess this might be an issue with if we've seen the node already, like if 3 was here first, it would just go to 3 and not visit 3 when it's in 1. So I guess maybe with scene, you would have to track both the node itself, and you would also have to track the number of delays, which I guess would start with 0, just because if this was, for example, 3 and this was 1, it would just go straight to 3, update max delay, and the node never be able to go to 3 again. So I think, yeah, in the scene, we would have to keep track of the node and the number of delays. So then I'll say here, if neighbor and delays +1 and not in scene. So if it's not in scene, then we could add it to scene. So I'll say add the neighbor. Oh, sorry, I should add it as a tuple. Add the neighbor and delays +1. I'm not sure why that's complaining. Do you know why there's the issue with this? Or is that just because I guess we haven't specified graph? Because it's of type unknown?
Set of tuple. You can ignore it. It's fine.
Okay. Okay. So of course I'll also have to add it to the queue. So I believe that's just append to add it to the end. And I'll add a neighbor and delays +1. So I think once we do all of this, this function should be complete because they'll iterate through every node and every delay, and then just return the one with the max delay. So I guess would it make sense to go through an example test case, or are there any questions, concerns, comments with the code?
We can go through an example.
Okay. I guess I'll just review this. So I could maybe copy this example input and hope I get the example output. So I guess I'll start at 0. I'll just have a scene data structure and a queue data structure. So with a scene, we initially have a 0, 0, and then likewise with the queue. And then we have the max delay, which is just set to negative infinity thus far. Okay, so the queue is not empty. So we pop from the queue, and then we'll say node is 0 and delays equals 0. So the queue is empty. So if the queue is empty, we check does the current node we're at equal the destination node? No, it doesn't. So we leave max delay as is, and then we iterate through all its neighbors. So I guess in this case we would add, we would first check if we would check if 3 and 1 isn't seen. It's not. So we would add it to scene. So I'll just say 3 and 1, add it to scene, and then add it, of course, to the queue as well. So once we add it to the queue, we'll do that for all the other nodes. I guess we can just duplicate this, change this to 2, change this to 1, and then add all these nodes to the queue as well. And once we do that, we've iterated through all the neighbors of that initial node. So we would go back to the top of the while loop, and we would pop again. So when we pop here, the first node was 3, so I guess the node becomes 3, and the delays becomes 1. And we check, does the node equal the destination node? Yes, it does. What's the max between 1 and a negative infinity? It's 1. So we change this to 1. And then we iterate through all the neighbors of the next node. So I guess maybe just to make it a bit shorter for the example test case or for the walkthrough, we can just have a graph like this. So then here we would just pop that 3, 1, of course. And then once we pop that, we would go through all the nodes in, I guess, sorry, we'd go through all the neighbors of 3, which don't exist. So this loop would, so I guess this would just never run or never go into it. And then we go to the next iteration of queues, which is 2, 1, and then 2, 1 again doesn't have any neighbors. So we would just delete that as well. Then we look at 1, 1. So we pop it, the number of the node would be 1, the delay would be 1. So once we pop that, we check, does the node equal the destination? No, it doesn't. Let's go through, so in that case, we would go through this inner loop, which is to go through all the neighbors of node 1, which is 3. We check, is 3 and 2 in scene? No, it's not. So we can add that to scene. So we can add that to scene, 3 and 2. And then we'll add it to the queue as well, 3 and 2. Then we iterated through all neighbors. So we'll end this iteration with node being 1, delays being 1. Go back to the top of the while loop, and what's in the queue? A node of 3 and delays of 2. We check, does a node equal the destination node? Yes, it does. So the max delay would be the max between the existent value, which is 1, and 2. 2 is a higher value. So I believe we would update the max delay to 2. And then we would iterate through all the neighbors of 3, which don't exist. The queue is empty. So then at the end of all of it, we would return max delay, which is 2.
Okay.
Did that walkthrough look right, or did I miss something?
No. That's good for now. Let's
Okay.
move to the time and space for this variant, and then we'll ask the second follow up.
Okay. So I guess the time complexity. So I guess we're not only going through all vertices and edges, but we're also going through or yeah, I think we are going through all vertices and edges. So the time complexity, I believe, was fine as is. But I think the space complexity would have to be updated because the both or the scene data structure, which consumes a greater amount of memory, not only keeps tracks of the vertices, but it also keeps tracks of the vertices and the number of delays. So I guess this would be O of V maybe times max delay, where delay is the maximum delay, which in this case was 2. So we're keeping track of all the vertices up to that max delay potentially, just because we're not only storing one instance of each vertice, but max up to max delay instances of each node or each vertices. Does that sound right?
How would you represent max delay as an input parameter?
Um, as an input parameter, that's, I guess, a good question. So I guess max delay would be up to, I guess, yeah, that would maybe be up to the number of vertices, just because in our initial example, we would have to go through every vertex to, or every node to reach that destination node. So
Okay.
then in that case, would it be O of V squared?
Okay. We can move on.
Okay.
All right. So the second variant of this problem is that now I'm going to tell you that you can assume there are no cycles, and
Okay.
then now I will also tell you that the edges have weights. So
Oh,
now,
okay.
in this variant, the distance between two nodes is not the number of jumps, but the sum of the weights between the two nodes.
Okay, so it would be the sum of the distances between two nodes. Okay. Um, okay, that's interesting. So I guess I should preface, I've never really experienced or seen a question on non-unweighted graphs. So how exactly would that be represented in the adjacency list? Would this just be a tuple where it would be the destination node and the distance from the source node to that destination node?
That would be fun for this problem. Yeah.
Okay. So I guess maybe you could just use the existing problem. Um, and then, sorry, I guess when someone asks a follow-up, do I just stay on the same problem or should I like have a new segment of code?
No, you can. Well, it's good to ask. For me, I don't care. You can go ahead and just reuse the same piece of code because it won't
Okay.
be relevant anymore. Yeah.
Okay, perfect. Thank you. Okay, that's good to know to ask in the future. So I guess here it would just be, for example, like 3 and 5, and then maybe like 2 and 7, 1 and 1, and we can just, to make it easy, say 2 and 1, 3 and 1, and then we'll just say here 3 and okay. So I guess in this case, the source node would be 0, the destination node would still be um, 3, and then there's multiple options. I think in the example we set here, it would make most sense to go from 0 to 2 instead of 1, just because it takes 7 steps to get to 2, um, and then go to 3 from there. And then that would be a total sum of 0 to 2 is 7 steps, and 2 to 3 is 10 steps. So that would be a total of 17 steps or 17 delays. And that's better than 0, 1, 2, 3, or 0, 3, because 0, 3 would be 5. 0, 1, 2, 3 would be 1 plus 1 plus 10, which would be 12.
Yeah.
So I guess in this case, would this be the expected output for this example input?
Yes.
Okay. Um, so I guess if that's the case, I think we can maybe just keep the algorithm as is with that BFS since we're going through every node. But what we would have to do is we would just have to, I guess, have instead of incrementing the delays by 1, we would have to increment the delays by the number of steps. Um, so I think if we think about it, um, the approach would still be the same. Still the same. Um, Only variation is update delays increment to account for the weight. Um, do you think that would be a good solution to proceed with?
Update the delay. Only variation is to update the delays increment to account for. So how would you update it?
So I guess here, like instead of saying delays plus 1, we
Yep.
would say delays plus this second value.
Okay.
Okay. So should I go ahead with implementing it?
Yep. We'll go ahead.
Okay, so I think the queue would still have the source and the delays. The scene would still have the source and the delays. This is the current amount of delays. And then here, this would include the neighbor and I guess you can say the distance. So we'll have to say delays plus distance. So for example, in this case, it goes to 3, then it checks have we, is 3 and at a distance of 5 in scene, which it isn't. So in that case, then we would add that here, and then we would add that to the queue. So then this updates delays not with 1 every time because we assumed it was unweighted and uniform distance, but rather with the delay that we see in the weighted graph. Um,
Okay.
as of now, I think that would work. Would it make sense to go through an example problem?
Yeah, let's go to your example that you gave.
Okay, so I'll just copy and paste this again. Um, so we have this example input, and let's see, what do we have? I'll just copy this really quickly. Okay, so we have a source of 0 and a destination of 3. And maybe to make this example easier, I'll just have something like this. Or wait, sorry. Yeah, I'll just have maybe something like this just to make it easier, I think. So we don't have to go through as many steps. Again, we start with 0 and 0. So I'll just say here 0 and 0. And then just copy this for the queue. So the queue is the same. Okay. And the max delay is again reset to negative infinity. So we pop a node and delays. So this would become 0. This would become 0. So check, is the destination equal to the node? No, it's not. So iterate through all the neighbors of 0. So check is 3 and 0 plus 5, which is 5 in scene. It is not. So then add that to scene, add to the queue. And we can do that for all the nodes. So I'll say 3, 5, 2, 7, 1, right, 1, 1. And then I'll add those to the queue as well. So then once we do that, we're iterated through all the neighbors of 0. And then we go back to the top of the queue. So at the top of the, and sorry, we did pop this earlier on. Okay, so once we have popped this, at the top of the queue is the 3, 5. So we check, so we pop it off the queue and update those member values, which is 3 and 5. So then we check, does it equal the destination node? Yes, it does. And set the max to the max between negative infinity and 5, where 5 would be the maximum value. Once that's done, we would iterate through all the neighbors of the current node in question, which is 3. And we check 3 doesn't have any neighbors. This iteration would end with the node being 3 and delays being 5, and we would pop up the next element in the queue. So then this would become 2, this would become 7. And then you would see here, go through all the neighbors of 2. So for 2, we only have one neighbor, and then we check here, does 3 and 17, or yeah, 3 and 12. Or sorry, yeah, 3. So the neighbor would be 3, and delays is 7. The distance is 10. So we check, is 3 and 17 and C? No, it's not. So we would add it here. 3 and 17. And then we would also add it here. 3 and 17. Once that's done, we've gone through all the neighbors of 2. So I think we're done through this iteration of the outer loop. We can proceed to the next one, which has 1 and 1. So 1, 1. So we pop 1, 1 is in the destination node. It doesn't have any neighbors. So we're done with this iteration. And then we go off with the next iteration. So this would be 3, and this would be 17. Um, Once that's done, we pop that off the queue, and then we check, is this a destination node? Yes, it is. So then find the max between the max delay, which is 5, and the current delays, which is 17. And then that equals 17, so update max delay. And then go through all the neighbors of this node, which is, oh, this the node in question is 3. There aren't any, so we end this iteration, we go back to the top, we check, is queue empty? Yes, it is. So in that case, we would return the max delay of 17. Um,
Okay.
was that walkthrough correct, or were we
That's fine.
missing something?
No,
Okay.
that's fine. So does the time and space complexity change versus the original prompt?
Um, no, I don't believe it changes because all we did to adjust for this variation was just replace the 1 with the distance in um, with the distance in the input, and again, C and Q before we're also storing the source and the distance. I guess while the time complexity might not change, the space complexity would change because we did say it was V times the max delays, which was previously set to just the number of vertices. But actually, I think, sorry, never mind. Even this time, I think we could potentially go through every vertex as well, or we would have to anyways. So I think actually it would be v squared because we would have to go through every vertex regardless of the distance because we're trying to find the max delay, not the min delay.
Okay. All right, let's call it here.
Okay, thank you.
And then we will go through some feedback now. Some feedback, some questions.
Okay.
So I usually start these off, asking you, how do you feel about your performance today? What do you think went well, and what do you think didn't go so well, if anything?
So I guess since I have nothing to back it on or like compare it to, I think maybe it went decently well. I guess I did forget maybe some of the syntax with where the libraries exist, and I think we made I realized some issues with like the Python fundamentals, like you can't have an immutable string or an immutable or a mutable type, sorry, for the hash map, and also I wasn't sure with how to change a character to lowercase. And then I guess yeah, I guess I didn't ask this verifying question of the weights when you initially presented the problem, so I guess I maybe missed some assumptions or clarifying questions that I made, but I shouldn't have assumed without asking.
Okay.
Um,
Yep.
and then I guess I don't know. I felt like maybe the walkthroughs were a bit slow, but I wasn't sure into how much detail to go into because I felt like for the first one I skipped a lot of detail, and then I think in the second one I like walked through it completely. So I
Yeah.
wasn't sure what to do.
Yeah, for sure. I think that's a pretty accurate assessment overall.
Okay.
I'll go over some notes I took as well, and we can chat about that. And you're free to ask any questions as well. It could be questions about the feedback. It could be questions about the problems. Anything. So,
Okay. Thank you.
so whatever you kind of see fit there. So I'll start with question one. So question one, obviously, this is a pretty simple problem, but the main thing here, I saw you brought your approach, your umpire approach. I think that's fine. One thing
Okay.
I will say is that I think you did have a pretty good read that some of your walkthroughs were too slow, right? And what does that really mean? Like, what it means for a walkthrough to be too slow is if you believe that the interviewer, or you believe that you already have high confidence in the algorithm, you can save time by doing a faster walkthrough with a simpler case, or by getting buy-in from the interviewer to check if they even want to walk through. Right. The main thing there
Okay.
is just that sometimes, especially if it's a simple problem, it's not meant to be very rigorous. Then it
Mhm.
doesn't really matter. Then the walkthrough matters a lot less.
Okay.
So don't. So I would say what I mean by that is, yeah. So the walkthrough, they were okay, but you're definitely err on the side of too long. And what that
Okay.
means is that you're robbing yourself of time to maybe do some more questions. That's the kind or
Okay.
any follow ups interviewer might have, right?
Right. Okay.
So group anagrams, I think that walkthrough was fine, but
Hmm.
you probably could have saved time. You probably could have saved time in the first place by just asking, hey, do we want a simpler case, etc.
Right. Okay. That does make sense. Okay.
Okay, let's take a look at that. So yeah, I think a positive thing again. Good to check assumptions. Good to check inputs outputs. Now for the first question, you actually did ask, what if the input list could be empty, and it could, and he didn't actually specify what the behavior there was. So that's
Oh,
one thing.
okay, yeah.
So one thing you just didn't follow up on there.
Okay.
Um, Regarding not knowing the import or not knowing the is lower function for character, I think most interviewers will let it slide. But
Okay.
I say this every time, right? But if the position is looking for Python, that's gonna be a cause for concern. If
Right.
you're using
Okay.
Python just for interview, that's fine. If they actually require Python skill, then that's gonna be a negative.
Right. Okay. That's a good point.
Okay, question. So question one's pretty whatever. Any concerns about that, or move on to question two?
No, I think that was very helpful feedback. Thank you.
Okay, question two is pretty straightforward as well. So this problem was, this is a very like you identified. This is a pretty standard graph search, right? Pretty standard graph search problem. Now, the approach you took for the first question was, I think, overall good. However, I don't think you're very familiar with the graph structures, and the reason I say that because there was a key assumption which you did not clarify, which is that the graph can or cannot have cycles. Right? If
Okay.
the
Yeah.
graph can have cycles, there cannot be an answer because you would just enter the cycle forever. So
Okay. Yeah.
this is a that would be considered like an error, right? So
Mm-hmm.
you didn't specify that. Now, of course, you had the scene set, but the scene set doesn't do anything. I didn't say you can't go to the same thing twice. I never said that.
Right. Yeah.
Okay,
Okay.
so that
That's
would
good.
be considered an error on that front. Okay. Um, right now the weights. So the weights. So like I said. So like you said, you didn't ask about the weights. That's actually that's not necessarily an issue. Typically speaking, now of course you should always ask about it, right? So whenever you get a problem about a certain input, there should be just a checklist of questions you ask. Right? You had this for the strings, right? List the string input. Can the list be empty? Can the strings be this character? Can the what character set? Right? So these are automatic questions you ask. Should be the same thing with graphs. Graphs, boom. Do the edges have weights? Boom. Are there cycles? Boom. Can they be negative weights? They're like these are immediate things you should just be asking me, like just automatically ask them regardless of the problem is about. If the question involves a graph, these questions should just be coming out, right?
Okay.
It's a
That's good to know.
cost it's a cost benefit analysis there because it takes so little time to ask it and write it down, right?
Right. Okay. That makes sense.
Now now aside from that, obviously the problem was pretty. I mean, it was well solved, right? So BFS makes sense. B plus D is correct. The space complexity there, yeah. So you did catch that. Yeah, you are storing every possible edge, and because cycles are allowed, that would be V squared. But
Right.
if but like I said, so that's kind of where that is. I think you're actually correct on that one. But the space complexity there, you got to be careful, right? If you're starting out with max delay, yeah, that's correct. But what is the max delay, right? How many times are you tracking the delay?
Right. Okay.
That's something you just got to be just got to be cautious of.
Right. Okay. That's very good to
Um,
know. Thank you.
right. So okay. But otherwise, the implementation was fine. The walkthrough was fine. The second time, the walkthrough was also pretty good. But like I said, I mean, like you said, right? It's a bit slow. You should check in. Do we really need to do this? What detail do we need to do this? And can we simplify that test case even further? Right. And you caught
Right.
yourself
Okay.
on that one on the first walkthrough for the second problem, where you simplified the test case. Right. That was good. But if you're
Mm-hmm.
doing that in the middle of the problem, you kind of already missed. Right. You should have done the beginning of
All
the
right.
walkthrough.
Okay.
Yeah. Second variation. Obviously, this one. So this one, yeah, negative. So this can it can have weights. It can have weights. One thing you didn't check, and it wouldn't matter in this case, but you didn't check is right. If the weights come in, you got to ask, can they be negative? Why is that
Right.
important? The reason that's important is because whether or not you have negative or positive or negative weights or positive only weights, that determines what algorithm you can use, right?
Right. Okay.
So that's going to be important. Now this is probably using BFS anyways. BFS works with all weights. That's fine, but
Okay.
that's not true necessarily for other graph algorithms.
Right. Okay.
Right, so you got to so like these questions just have to come out.
Okay. Good to know.
All right, so for practice, you should, I mean, obviously go back and form the questions for the graphs, and this should be true for, so like for example, if a tree question comes out, you should have automatic questions about trees. Right, if it's a heap question, come on that. If it's a pointer question, come on about that. Right, so like no
Right.
matter what kind of question it is, you should just have probably like like 2 to 5 questions that just are that just come out immediately for that.
Right. Okay. That's very good to know. Thank you.
All right. The only other thing I will say is about yeah. So we did run out of time for the second follow up. The This was supposed to build up to the real question, which was, um, how would you solve this problem? But the destination node is every node. So can you find the longest node between a source node and all other nodes? That would be
Oh.
like the
Okay.
real question, which would be a medium difficulty question, right? The way
Right.
it's asked right now is fairly simple. You could some people might say it's a hard or easy, some people might say it's an easy or medium, but the real
Mm-hmm.
medium question here would be what is the write a function that finds the longest path to all nodes given one source node. So you could do that for
Right.
homework.
Okay. Yeah, that would be a good idea. Thank you. Okay. Um, so thank you for all that feedback. Would you say like with the umpire framework that I learned, like was it into too much detail? Did it eat too much time? Should I have spent more time coding, less time planning, or vice versa?
So I think that would be something which you have to read depending on the type of interview. I'll give you an
Okay.
example. So if you're going for an interview like let's say it's a Meta Loop or Amazon Loop, they're going to be asking two questions, two mediums. You can assume it's two mediums or one medium, one hard. You really won't
Mhm.
be asking if you get asked two hards, that's unlucky. Don't plan for that.
Okay.
You should be planning for one medium and one hard, and you
Okay.
realistically be asked two mediums. If you can't use the Empire framework to solve one medium and one hard in 50 minutes, it's either the framework is too slow, it's being held back too much, or you're not very familiar with the framework. You don't know where to cut the corners. So I
Mm.
wouldn't be quick to kind of blame the framework either way on this kind of thing. But or like even if you didn't have the umpire framework, you still should do walkthroughs if it's a difficult problem if you're not sure about the edge cases, right? But
Mhm.
um, either way, either if you use this framework or another framework, you have to be able to solve one medium, one hard in 50 minutes if that kind of company's your goal, right?
Right. Yeah. I guess yeah. My current technical ability is far from that. Now, if these were easy questions. Okay. So yeah, I guess that's good to know. And then I guess for my example walkthroughs, since they take so long, do people usually with walkthroughs walk through multiple walkthroughs, like multiple? I guess as you just mentioned, edge cases.
The main
Is
thing
that
here
something that should
is
be done?
yes. The main thing here. So the real purpose of the walkthrough is twofold. The first thing is if the interviewer is not convinced you are correct,
Okay.
so they will make you walk through it because they want you to find the bug. That's the first reason. The second reason, well, I mean, and that's the most common reason
Yeah.
because the fact of the matter is that most interviewers know all possible ways to solve the problem. They don't actually like they know if it's correct or not. The second reason is sometimes because they want you to check an assumption. So it's not an implementation issue, is that they want to check your problem understanding issue, which is that you have not made a correct assumption, and they want you to
Okay.
walk through it to detect that the problem is not like the problem you're solving is not the problem that has been asked. So generally speaking, you won't be asked to walk through questions at a high detail. They'll be asked to just say, do you think it's correct? Okay, we're moving on then. So so more often than not, what I'm saying is, if you don't think there's an issue, if you think there's an issue, then you should walk through it so you can fix it yourself. If you don't think there's an issue, then you should ask them, hey, I'm convinced this is correct. Do you think so? Can we move on? Or do you want to walk through?
Okay. So if I don't think there's an issue, then ask them if they want to walk
Yes.
through. If I think there might be something wrong, it's better if I say, I think we should do a walkthrough to confirm if it's correct.
Yes. Exactly.
Okay.
And you
Okay.
should make yourself a test case which proves or disproves that concern. So, for example, right, in your test cases, you didn't have any cycles, which means that you either don't know about
Right.
cycles, which is unlikely, or you just didn't think that that could be part of the problem.
Okay. Yeah. Right. That's a good point. Okay. That's good to know. Okay. Thank you. Um, okay. Yeah. Thank you so much. Yeah. This was incredibly helpful. Thank you so much for doing this for free. I know other services charge you an insane amount of money for mock interview, so I really appreciate all this feedback. Thank you so much.
No worries at all. Cool.
Okay.
Thank you for participating.
Yeah.
Take
Thank you
care.
so much for doing this.